Hi everyone, this is Ehsan. Welcome to my channel. In this presentation series, I'm going to see into the special window into the board of industry. My goal is to bridge the gap between scientific knowledge and real-world industrial application. Today we began exploring one of the most powerful tools in engineering, computer-aided design. This topic is deeply rooted in the foundational book, the NURBS Book by Les Piegl and Tiller, widely considered a gold standard for understanding curve and surface in computational geometry, CAD, and animation. We'll go through chapter by chapter. As you can see in this slide, there are 12 chapters in total. We'll start with chapter 1, which covers the basic of curve and surface, essential knowledge for any engineer, designer, or math enthusiast. So whether you're a professional in the field or just passionate about design and geometry, this series is for you. Let's get started. Chapter 1 covers several foundational concepts including implicit and parametric form, power basis form of a curve, Bézier curve, rational Bézier curve, tensor product surface, and it concluded with a set of practical examples. In today's presentation, we'll focus on implicit and parametric form, which are fundamental to representing curve and surface in space. These forms serve as the mathematical language behind many design and modeling systems, and understanding them into the first step toward mastering computational geometry. Let's delve in the topic. Let's begin with the fundamental difference between implicit and parametric curve. An implicit equation of a curve is typically written in form of f equals 0, for example in 2D space. This means the curve is defined as the set of all points that satisfy this equation. On the other hand, in a parametric equation expresses the curve using a independent parameter like u in parameter space. The curve is described as cu equal xu yu in 2D space, where u vary from a to b. For example, consider a circle with radius 1. In implicit form, we have f equal x2 plus y2 minus 1 equals 0. And in parametric representing form, cu equal cosine u sine u, where u vary from 0 to pi divided 2. Both representation describe the same geometry, a segment of unit circle, but in very different way. While the implicit form define a curve as a constraint in x and y, the parametric form explicitly trace the curve by varying parameter. This make parametric representation for more useful in 3D modeling and computer graphic, where precise control over surface generation, motion, and animation is required. You can see the power of parametric curve in action in many modern graphic and CAD software application. It is a foundational concept in those systems. One important feature of parametric representation is that it's not unique. The same geometric curve can be represented by multiple different parametric equations. Let's return to the example of a circle. For a quarter circle, both of the following parametric equations describe the same curve segment. Even though they look different, see at above and CT as at down of this slide, both trace out the same part of unit circle, a quarter from 1 0 to 0 1 into the Cartesian. As you can see in the figure I generated using MATLAB, both parameterization result in the same geometric shape. This flexibility is parametric design is extremely useful in CAD and animation, where different representation can be optimized for different needs, such as computational efficiency, control point manipulation, or animation timing. Now let's talk about velocity along a parametric curve. For a parametric curve, the velocity is simply a derivative of the position vector with respect to the parameter. Let us start with the unit circle using the standard parameterization. C prime, the magnitude of the velocity vector is 1. Since the magnitude is always 1, the speed constant. This is known as uniform parameterization, where the motion along the curve happen at a steady rate. Now let's look at different parameterization of the same vector, this time using a parameter t in parameter space, C prime 2. The speed or the magnitude of the velocity vector is 2 divided 1 plus t2. In this case, the speed varies with t. As t increases from 0 to 1 in parameter space, the denominator grows and the particle slows down as it moves along the curve. This example shows an important concept. Different parameterization affect how an object moves along the same geometric path. While the shape of the curve doesn't change, the motion along it does. In applications like animation, motion planning, and CNC machining, controlling this speed is crucial. Now let's move from curves to surface representation. Take a sphere of radius 1 as an example. In implicit form, the equation is as x2 plus y2 plus z2 minus 1. In parametric form, we use two independent parameters, u and v, in parameter space. The parametric equation are x, y, and z component as depicted in the slide. You can see the mathematical visualization showing both implicit and parameter space form of the sphere. Even though the equations differ, they describe the same surface geometry. Here you move vertically and we move horizontally. And this is the parameter space of u and v. While the parametric representation of a sphere work well in most regions, it introduced a special challenge at the north and south pole, where u equal 0 and u equal pi. At this point, the longitudinal tangent vector sp becomes 0, meaning there is no well-defined direction along the longitude. As a result, the surface normal vector become undefined or unstable, causing problem in application like lighting, rendering, and surface analysis. To understand this more precisely, we define the partial derivative of the surface S as Sv, the latitude velocity and longitudinal velocity at any regular point on the surface. There is where the cross product Su cross Sp does not vanish. We can compute the unit normal vector as n, but again at the pole where Sv equals 0, the cross product becomes 0 and the normal vector is undefined. This is a common example of how singularity in parametric surface can impact geometric computation. We've seen how both implicit and parametric representation can describe curve and surface, but is one always better than the other? Not necessarily. In geometric modeling, we often use both approaches because each has its own advantage and limitation depending on the task application. So let's break it down. One major advantage of parametric representation is that extend naturally into 3D, from 2D space to 3D space. For example, if we want to define a 3D curve, we simply add z component and find cu equal xu, yu, and zu. This makes parametric form especially powerful for designing 3D curve and surface in computer graphic and CAD system. In contrast, implicit curves are usually restricted to 2D plane like the xy plane, xz plane, or yz plane. Extending them into the 3D space often requires more complex formulation. Another key difference between two representations is how they handle boundedness. Parametric curves are naturally bounded simply by defining a range for parameter u. You can control exactly where the curve starts and ends. In contrast, implicit curves extend infinitely unless you apply additional constraint. For example, consider a line defined by ax by plus c equals 0. Another significant advantage of parameter curve is their natural direction of traversal. As depicted in the figure on the slide, moving from A to B in parameter space, resulting the curve began trace from CA to CB. This directional property is especially useful in animation, robotic, and CAD modeling, where control movement along a curve is essential. Implicit curves, by contrast, does not possess this property. Parametric representation are inherently more intuitive for design, especially in computer-aided design and 3D modeling. Unlike implicit curve, parametric curve, such as Bézier and B-spline curve, are defined by control point, giving designer directed and flexible control curve control over the shape. This makes parametric curve ideal for interactive design workflow where precision, adjustability, and smooth transformation are essential. In industrial such as automotive styling, architectural modeling, and animation, parametric modeling support both artist intent and engineering precision, enabling seamless inherent and real-time shape manipulation. The complexity of mathematical operation depends on the method of representation. If you need compute a point on a curve or surface, parametric form are much easier. If you check whether a point belongs to a curve or surface, implicit form are simpler. As mentioned in a previous slide, one challenge with parametric surface is parametric anomalies. For example, on a unit sphere at the pole pole u equal 0 and u pi, the longitudinal tangent velocity sv vanishes, making normal computation tricky. This is purely a mathematical issue, not a geometric one, because the normal still exists. So what's the takeaway? Neither implicit nor parametric form are inherently better. They both have a standard and weakness. Implicit form are great for general shape definition and point inclusion test. Parametric form are more flexible, easier, and better suited for design and modeling. For this reason, modern CAD and animation and computational design focus heavily on parametric method. That's why in the rest of the book we will almost exclusively use parametric representation. Up to next we explore beauty of Bézier curve and how they shape modern design. I hope this gave you a clear understanding of why parametric form dominate in geometry and modeling. If you find this helpful, like the video to support the channel. Got question? Drop a comment below. I'd love to discuss them you. And do not forget to describe. We dive into Bézier curve, the foundation of model curve. Modern curve in modeling. See you in the next video. Have a nice time. Bye bye.